This lesson, we're going to learn how to distinguish odd and even functions, both graphically and algebraically. The graph of an odd function has rotational symmetry about the origin. This means if we rotate the graph 180 degrees along the center at the origin, the graph will be exactly the same. In other words, we could say we reflect the graph along both y-axis and the x-axis, and we will have the same graph. The graph of an even function is symmetric with respect to the y-axis. This means that the function is cut evenly at the y-axis, and each half is an exact mirror of the other. Please note that odd function is not necessarily an odd degree function. Likewise, an even function is not necessarily an even degree function. Similarly, an even degree function may not necessarily to be even function. An odd degree function may not be necessarily an odd function. Example 1. We are going to do an investigation on the graph of an even function to develop the algebraic formula for the even function. The given function f is an even function. That means the graph needs to be symmetrical about y-axis. Look at the first point, -2 and 1. Because it has to be even, that means we have to have a point right on 2, 1 in order for them to be symmetrical around the y-axis. Next point, -1 and 3. That means we need to have another point at 1 and 3 in order for them to be symmetrical around the y-axis. Next point, 0, 0. Since it is already on the y-axis, so there's no need to add another point. And the fourth point is at 3, 2. In order for them to become symmetrical, then we need to have a point at -3 and 2. The last one is at 4, 1. In order for them to become symmetrical, that means we need to have a point at -4 and 1. Now, let's take a closer look. On the last point, we have 4 and 1, and the symmetrical point will be at -4 and 1. So using function notation, we write f at 4 equals 1. That means when x equals 4, y is 1. The other point, f of -4 equals to 1. And they both have the same y values. That means f of 4 equals to f of -4. Let's look at the last second point. We have 3 and 2. The symmetrical point will be at -3 and 2. Once again, 3 and 2 can be written as a function notation. F at 3 equals to 2. This means when x equals to 3, y is 2. And the other point, we can write f of -3 is also 2. So they have the same y values. That means we can say f at 3 equals to f of -3. Therefore, we know a function is even when fx equals to f of -x. That means when the x value multiplied by a -1, the y value stayed the same. Therefore, we say an even function occurs if and only if f of x equals to f of -x. Example 2. Now, let's do an investigation on the odd functions to see what the algebraic formula will look like. First point, we have -2 and 1 because our function is symmetrical along the origin. That means if you rotate 180 degrees, they will have the same graph. That means the point must be here. So the point will be 2 and -1. And next one, we have -1 and 3. Once again, rotate 180 degrees, it will become here. That means 1 and -3. The next one, 0, 0, is on the origin. So if we rotate 180 degrees, it will stay here. And next one, we have 3 and 2. If you rotate 180 degrees, you end up here, which is -3 and -2. The last one, we have 4, 1, and that's rotate 180 degrees. You will become -4 and -1. Let's use the last point to develop the formula. So we have the point 4, 1, and the reflected point will be at -4 and -1. This means f at 4 equals to 1, and f at -4 equals to -1. As you can see, those two y values, they are not the same. One is positive, one is negative. So I'm going to multiply by -1 on both sides of the equation. Now I get a positive 1. So this means 1 equals to f at 4 equals to negative of f of -4. That means f at 4 equals to negative f of -4. So using the x to replace the 4, we get fx equals to negative f of -x. And this is so-called the odd function. Example 3. Determine graphically whether the following functions are even, odd, or neither. Remember, even is symmetrical around the y-axis, odd is a rotational symmetry, neither is not even and not odd. Part A. This graph looks like it has a rotational symmetry. Let's use a point to check. Here, the point is at 2, 5. If it is odd function, then the point -2 and -5 needs to be on the graph. As you can see, -2 and -5, it's not on the graph. Therefore, this is a neither. Part B, we can see the graph is symmetrical around the y-axis. Therefore, it is an even function. Part C, this is a parabola, which is also symmetrical around the y-axis. Therefore, part C is also an even function. Part D, the graph looks like it has a rotational symmetry. Let's use a point to check. The point here is 2, 3, and the point -2, -3 is also on the line. Therefore, it is an odd function. Part E, this graph also looks like it has a rotational symmetry. Let's use a point to check. The point here is 1, 6. -1, -6 is also on the line. Therefore, part E is also an odd function. Part F, it is not symmetrical around the y-axis, and it doesn't have the rotational symmetry. Therefore, neither. Example 4. Now we're going to determine algebraically whether or not each function is even, odd, or neither. Question 1. Let's replace x with a -x. Then we get -x whole thing squared, which is x squared. Because fx equals to f of -x, therefore it is even. Question 2. Once again, we find f of -x first, and we are going to expand and simplify it to be -x cubed plus 2x. As you can see, fx and f of -x right now, they are not the same thing. Therefore, we're going to multiply it by a -1, which will become negative of -x cubed plus 2x, which will become x cubed minus 2x. And now, those two equations are the same. Therefore, we say, because f of x equals negative of f of -x, therefore, it is an odd function. Question 3. Once again, let's find f of -x first. Then we're going to expand and simplify it. We get x squared plus 3x plus 4. Compare those two equations. They are not the same thing. So we're going to multiply by another -1. Then we will get -x squared minus 3x minus 4. Once again, compare those two equations. As you can see, they are not the same. Therefore, they are not even, they are not odd. So we say this function is neither. Let's do a shortcut. When all the exponents are odd number and without the constant term, then it is an odd function. When the exponents are all even numbers, with or without constant term, it will be an even function. So let's look at example 1. We have an even exponent with a constant term. Therefore, it is even. Question 2. The exponents here are 3 and 1. They are both odd and there is no constant term. Therefore, odd. The question 3, the exponent here is 2 and the next one is 1. Because those two exponents, they are not the same thing already. This is even, this is odd. So we know the function is neither. The shortcut only works if the function is a polynomial function. So let's look at example 5. None of the functions here are polynomial function. So we have to use the formula for even and odd to check. Part A. Let's check for even first. So we do f of negative x. After we expand and simplify it, we can see those two equations are not the same thing. That means it is not even. Then we times by another negative to see whether or not it is odd. Then we can see those two equations are the same. Therefore, we say fx is an odd function. Part B, let's do g of negative x to check for even first. As you can see, you have a 1 minus x inside the square root, whereas the original equation has 1 plus x inside the square root. Therefore, those two equations are not the same. It is not an even function. Next, we multiply by another negative 1 to see whether or not it is an odd function. And as you can see, those two equations are not the same either. Therefore, we say this function is neither. Part C, now we have an absolute function, but the way to check it is the same thing. So let's find h of negative x first. Then you will see absolute of negative x minus 1. Since absolute value never returns a negative value, that means absolute of negative x is actually the same thing as absolute of x. Therefore, you can see those two functions are the same. Therefore, we say it is an even function. Example 6. The portion of the graph of fx is given where x is greater or equal to 0. We want to draw the part of the graph where x is smaller than 0. So part A, if the function f is even, then the graph will be symmetrical around the y-axis. So the graph should end at this point with the maximum height around this point. And now let's connect the pink dots using a semicircle. That's our even function. Part B, if the function f is odd, then it should be a rotational symmetry. That means if we rotate 180 degrees above the center of the circle, which is at the origin, we should have the same graph. This implies we should end at this point, and with the minimum approximately at this point, and connect the pink dots using a semicircle. Now that's our odd function.